Okay, so a vector is going to have both magnitude and direction, all right? Examples are velocity and force. So in the case of velocity, okay, if you have, for example, a velocity of 5 miles an hour west, okay, that number, 5 miles an hour, is your magnitude. West is your direction. Okay, the combination of magnitude and direction make up your vector.
Is that just specified to like cardinal direction, north, south, east, west, or can it be like?
It could be any direction.
Like negative and positive also correct?
Any direction. So let's go through the lesson and you'll see exactly what we're talking about. Okay, so velocity is a vector, force is a vector. If a quantity has no direction, just magnitude, it's a scalar. All right? So for example, if a certain object is moving 6 meters per second east, that's the velocity. The speed is simply 6 meters per second. Okay, so when you look at your speedometer and you're going 72 miles an hour, that's your speed. If you're driving 72 miles an hour north or northwest or southeast, that's your velocity and it's a vector quantity. So let's move down here and let's see if each of these are vector or scalar quantities. The first one is a ball thrown northwest at 60 meters per second. This is a vector. A tennis ball served at 110 miles an hour. Scalar. A sprinter running north at a certain, it's blocking, it's a vector.
I have a question.
Yes.
So scalars lack direction?
Yes.
Okay.
Okay. We represent vectors pictorially by an arrow. You can also see it called a directed line segment. All right. Now, if you look at a vector, there are some characteristic features here. This point here is the initial point, or we call it the tail. All right? B is the terminal point, also called the head, also called the tip. I normally use tail and head, okay, as opposed to initial point and terminal point. Okay, notation. It's AB with a single arrow. So if we're writing it by hand, it's AB and the arrow looks like this. Or it'll be lowercase a and the same arrow.
You don't draw like an arrow, you just draw the top part of the arrow?
It's just a single-sided arrow. In print, it's a bold A. Okay, so when we're writing a vector, we can't make it bold. It's going to be
What if you just color it
like
in?
this. Okay, this is the notation we're using.
We can't use
Right.
AB with the line.
Either or. Most of the time, you're not given A and B. You're just given the name of the vector as lowercase a. Okay? All right. If you take your vector and put it on a set of x and y axes, if you put it at the origin, then we say the vector is in standard position. Okay? The initial point is at the origin here. So how do we define the direction of the vector? The direction is now going to be the angle between the x-axis and the arrow. Okay? If you don't have it specifically on the x-axis or the y-axis, if you just have your vector up in the air like this, then you can still draw a horizontal line, and this angle is the direction of the vector. Okay, so it doesn't always have to be, in the north, south, east, west. It can obviously be anywhere on the circle. Okay? The magnitude is physically the length of this arrow. So it's the length of the line segment, and we give magnitude by absolute value of A. So if we were writing it in shorthand, it would be A in absolute value bars.
Okay.
Now, in this case, you have a scale given. It says that every centimeter is 5 feet per second. So if you took a ruler and measured this, it turns out that it's about 2.6 centimeters. Meaning, this vector represents a quantity which is equal to 2.6 times 5, right? Because each centimeter is 5 feet per second. If this is 2.6 centimeters, then it's 2.6 times 5 feet per second.
So it's like a map.
It's exactly like a map. So this is 13 feet per second.
Maybe centimeters per second?
Okay? Each centimeter represents 5 feet per second. Each centimeter represents 5 feet per second. Okay, so that's the magnitude of vector A. Bearing. This is something we hear all the time when we're talking about direction. When you're talking about a boat traveling down a stream, when you're talking about a plane traveling in a certain direction, we use terminology like bearing, quadrant bearing, and so on.
What is phi?
Okay, so a bearing, okay, a quadrant bearing is given the symbol phi. The way you write phi is like this. It's a Greek letter, just like theta and so many others that we use in math. All right, the quadrant bearing is always going to be between 0 and 90 degrees. And the way you measure it is, if this is your vector, you draw a north-south line at the tail of it, and the angle between the north-south line and your vector is the bearing, okay? So if you draw the vertical line, the angle between the vertical line and your vector is your phi,
What about the other?
okay? In this case, this is vector V. It's 35 degrees east of the southern direction, the south direction. So we say it's south 35 degrees east. Now if you see something like this, the way you would draw it is, you have south 35 degrees east. So you have a line going south, and if you go 35 degrees east from it, there is your vector. Okay? Sometimes it's useful to give true bearing. For that one, you start from the north and you go all the way down. In this case, you're going to pass 90 degrees sometimes. So true bearing is always expressed in 3 digits. If you have a vector that's 25 degrees from the north, you write it as 025, okay, just because you have to have 3 digits. So if your vector looks like this, you draw a north-south line, and suppose you measure this angle and it turns out that it's 31 degrees, then the true bearing would be 031 degrees. All right? Questions?
Wait. How is it 031 degrees? I'm sorry.
You always have to express it in 3
You always have to do 3
units,
digits?
in 3 digits for the true bearing.
Okay.
Okay. Here we have a couple of vectors. They each have their labels A, B, C, D, and so on and so forth. When we talk about parallel vectors, they have either the same direction or opposite direction, but they are not necessarily going to have the same magnitude. So let's find some of the parallel vectors in the diagram.
A,
You have A parallel to what?
B,
To B,
and C,
and to C,
and E,
and to E,
and F.
And
and to F.
Yay.
and B.
Okay, so all of those are parallel. They're going in the same direction or an opposite direction, and they don't have to have the same magnitude, but they have the same angle with respect to the horizontal.
Would they have
Okay?
the little arrow thing?
No.
Why?
they will have specified their degree from the horizontal, okay? It's not geometry, you don't have the little arrows.
Oh, so how can we put it before?
No, he means the arrow for the parallel.
Oh, no. I meant the arrows on top, like
Yeah,
the
Any
triangle.
vector must have this arrow here. Any vector, otherwise it's a segment, it's
No,
not a
I mean, when
vector.
we write A is parallel to B, would we have?
Right, you guys are talking about completely different things.
Okay.
Talking about the same.
No for you, yes for you.
Okay, so we put a little arrow above
Yes.
each A, B, C, D, E.
Yes. Here, yes.
That's what
Okay.
I was asking.
Okay, sorry then. Yes.
Well, there's some hard arrows to draw.
Okay, equivalent vectors have got to have the same magnitude and the same direction. Alright, so in this case, for example, A and C are equivalent vectors.
And that's it, that's it.
And B, what about B?
No, B, because it's not the same magnitude.
Opposite vectors have the same magnitude but opposite directions. So for example, C and E have the same magnitude but are going in opposite directions. The way we write that is we say vector E is the negative of vector A. Okay? So vector E is the negative of vector A, meaning they are opposite vectors. So that was a lot of terminology, vocabulary, and so on and so forth. Vectors never act alone. Vectors are always reacting with other vectors, or interacting rather with other vectors. So most of the time, okay, we have to combine two or more vectors, and we have to find what we call the resultant vectors. The resultant vector is the sum that we obtain when we add two or more vectors. There are two ways to find resultant vectors: the triangle method or the parallelogram method. I like the triangle method better. I think it's more straightforward. All right, so what we do is this. You have your vector A and your vector B here. What needs to happen is one is your first and the other is your second vector. What you have to do is you have to put the tail of B to the tip of A. Okay? So the tail of B to the tip of A. Now, vectors, all right, their characteristic is their direction is part of their characteristic. So you can take vectors and you can move them sideways, up and down diagonally, but you are never, ever, ever allowed to rotate or to change the angle by even a split degree. Okay? But you're more than welcome to move them anywhere you want in space. All right? So what we do here, if this is vector A and this is vector B, you bring them together so that the tip of the second one is at the tail of the first one. Once you do that, you draw a resultant vector here, and that's the sum of the two vectors. Okay? Now, if we draw these precisely using a ruler, all right? If you draw this precisely and that precisely, then all you have to do is, again with a ruler, measure that resultant vector, and that's your answer. Okay? Huh? Yeah.
So the hypotenuse is A plus B.
The resultant, not hypotenuse, resultant.
Oh, the resultant. Okay.
Okay. So here it says find the resultant of each pair of vectors using either the triangle or parallelogram method. You want to state the magnitude to the nearest centimeter and the direction relative to the horizontal. So for this, you're going to have to use a ruler and a protractor.
I don't have a.
Okay. So for homework, you have to use it. I will bring some for the test, but for the homework, you have to use your own. All right. What you're going to do here, you have V and W. Okay? You're going to put the tail of the first one at the tip of the tail of the second at the tip of the first. Okay, so we're gonna reproduce